Reinforcement learning, artificial intelligence, schooling, and GED study tips. Written by David Veldspar. Narrated by Jason R. Gray. Introduction. Reinforcement learning is one of the most active research areas in artificial intelligence. Reinforcement learning is training by rewards and punishments. Here, we train a computer as if we train a dog. If the dog obeys and acts according to our instruction, we encourage it by giving biscuits, or we punish it by beating or scolding. Similarly, if the system works well, then the teacher gives positive value, or in other words, reward, or the teacher gives negative value, in other words, punishment. The learning system which gets the punishment has to improve itself. Thus, it is a trial and error process. The reinforcement learning algorithms selectively retain the outputs that maximize the received reward over time. To accumulate a lot of rewards, the learning system must prefer the best experienced actions. However, it has to try new actions in order to discover better action selections for the future. Temporal difference learning. Temporal difference learning is a central idea of reinforcement learning. It is based on Monte Carlo methods and dynamic programming. It is an unsupervised technique. Temporal difference learning methods can learn directly from raw experience without a model of the environment's dynamics. Examples are learning to play games, robot control, elevator control, network routing, and animal learning. Applications of reinforcement learning. Personalization Travel Support System is one software that is designed to provide traveling information as per the user's interests. It applies the reinforcement learning to analyze and learn customer behaviors and list out the products that the customers wish to buy. If the system selects the right item that the customer wishes to buy, then it is given reward by assigning a particular value for the state that a user selects to perform. And if the system selects an item which the user does not wish to buy, then it is given a penalty. This way, the system learns the personal interests. In this process, the system acquires the knowledge of the user behavior and interest, which make it decide which information should be given to a particular user. This results in greater customer satisfaction and increases in the success rate of product promotion. Reinforcement learning. What does reinforcement learning mean? Reinforcement learning, in the context of artificial intelligence, is a type of dynamic programming that trains algorithms using a system of reward and punishment. A reinforcement learning algorithm, or agent, learns by interacting with its environment. The agent receives rewards by performing correctly, and penalties for performing incorrectly. The agent learns without intervention from a human by maximizing its reward and minimizing its penalty. Reinforcement learning is an approach to machine learning that is inspired by behaviorist psychology. It is similar to how a child learns to perform a new task. Reinforcement learning contrasts with other machine learning approaches in that the algorithm is not explicitly told how to perform a task, but works through the problem on its own. As an agent, which could be a self-driving car or a program playing chess, interacts with its environment, receives a reward state depending on how it performs, such as driving to the destination safely or winning a game. Conversely, the agent receives a penalty performing incorrectly, such as going off the road or being checkmated. The agent over time makes decisions to maximize its reward and minimize its penalty using dynamic programming. The advantage of this approach to artificial intelligence is that it allows an AI program to learn without a programmer spelling out how an agent should perform the task. Why reinforcement learning? Motivation. Reinforcement learning allows the machine or software agent to learn its behavior based on feedback from the environment. This behavior can be learned once and for all, or keep on adapting as time goes by. If the problem is modeled with care, some reinforcement learning algorithms can converge to the global optimum. This is the ideal behavior that maximizes the reward. This automated learning scheme implies that there is little need for a human expert who knows about the domain of application. Much less time will be spent designing a solution, since there is no need for handcrafting complex sets of rules, as with expert systems. And all that is required is someone familiar with reinforcement learning. How does reinforcement learning work? Technology. As mentioned, there are many different solutions to the problem. The most popular, however, allows the software agent to select an action that will maximize the reward in the long term, and not only in the immediate future. Such algorithms are known to have an infinite horizon. In practice, this is done by learning to estimate the value of a particular state. This estimate is adjusted over time by propagating part of the next state's reward. If all the states and all the actions are tried a sufficient number of times, this will allow an optimal policy to be defined. The action which maximizes the value of the next state is picked. When does reinforcement learning fail? Limitations. There are many challenges in current reinforcement learning research. Firstly, it is often too memory expensive to store values of each state, since the problems can be pretty complex. Solving this involves looking into value approximation techniques, such as decision trees or neural networks. There are many consequences of introducing these imperfect value estimations, and research tries to minimize their impact on the quality of the solution. Moreover, problems are also generally very modular. Similar behaviors reappear often, and modularity can be introduced to avoid learning everything all over again. Hierarchical approaches are commonplace for this, but doing this automatically is proving a challenge. Finally, due to limited perception, it is often impossible to fully determine the current state. This also affects the performance of the algorithm, and much work has been done to compensate this with perceptual aliasing. Who uses reinforcement learning? Applications. The possible applications of reinforcement learning are abundant, due to the genericness of the problem specification. As a matter of fact, a very large number of problems in artificial intelligence can be fundamentally mapped to a decision process. This is a distinct advantage, since the same theory can be applied to a much different domain-specific problem with little effort. In practice, this ranges from controlling robotic arms to finding the most efficient motor combination, to robot navigation, where collision avoidance behavior can be learned by negative feedback from bumping into obstacles. Logic games are also well suited to reinforcement learning, as they are traditionally defined as a sequence of decisions. Games such as poker, backgammon, Othello, and chess have been tackled more or less successfully. Where can I find out about reinforcement learning? Well, you've come to the right place. The Reinforcement Learning Warehouse is a site dedicated to bringing you quality knowledge and resources. We have a wide selection of tutorials, papers, essays, and online demos for you to browse through. Then, it's just a matter of finding a problem you want to solve and applying all you've learned. Reinforcement learning, or RL, is an area of machine learning inspired by behaviorist psychology, concerned with how software agents ought to take some actions in an environment so as to maximize some notion of cumulative reward. The problem, due to its generality, is studied in many other disciplines, such as game theory, control theory, operations research, information theory, simulation-based optimization, multi-agent systems, swarm intelligence, statistics, and genetic algorithms. In the operations research and control literature, the field where reinforcement learning methods are studied is called approximate dynamic programming. The problem has been studied in the theory of optimal control, though most studies are concerned with the existence of optimal solutions and their characterization, and not with the learning or approximation aspects. In economics and game theory, reinforcement learning may be used to explain how equilibrium may arise under bounded rationality. In machine learning, the environment is typically formulated as a Markov decision process, or MDP, as many reinforcement learning algorithms for this context utilize dynamic programming techniques. The main difference between the classical techniques and reinforcement learning algorithms is that the latter do not need knowledge about the MDP, and they target large MDPs where exact methods become infeasible. Reinforcement learning differs from standard supervised learning in that correct input-output pairs are never presented, nor suboptimal actions explicitly corrected. Instead, the focus is on online performance, which involves finding a balance between exploration of uncharted territory and exploitation of current knowledge. The exploration versus exploitation trade-off in reinforcement learning has been most thoroughly studied through the multi-armed bandit problems and in finite MDPs. Homeschooling: How to reinforce learning. You may wonder how much practice your child needs in order to maintain knowledge and skills. Some curriculum provides pre-tests, quizzes, and post-tests that can be used to test and reinforce concepts that have been learned. For example, spelling power provides a continual review. Thus, as words are repeated, you can determine whether your child knows how to spell the word or not. Saxon Math is another curriculum that teaches new material, gives some practice of the new, but the whole assignment is a review. Straightforward English and Math from Garlic Press also have pre-tests, practice sheets, and post-tests. Spelling can be a real challenge. It seems that students are either very good or very poor spellers. Those students who have good spelling skills can learn with any curriculum and methods. However, as you may know, if a student struggles with spelling, finding a curriculum or method of teaching spelling is very difficult. One solution is to use a multisensory spelling curriculum. If you have only one student, a spelling program that fits the child's learning style will work. However, many homeschooling families have more than one child. Using a multisensory program will fit every child. The kind of activities that people use to learn spelling words include saying each letter and each syllable, tracing on or in a rough surface, like sand, on a rug, sandpaper, etc., or in the air with big motions, writing a number of times, and spelling it out loud. Visual learners can draw a line around the word to see the shape of the word. Another component of a good spelling program is the test, study, retest approach. In many programs, students are given a list of 20 words. Good spellers already know most of them, and those who struggle cannot possibly learn them all. With the test, study, retest method, you test the student to find a few words that he needs to learn. Then, the student studies using all the senses and takes the test again. Continue on ones that are missed and go on to new ones a few at a time. A spelling program should provide frequent review and use words that the students will actually use. You can adapt many spelling curriculums to these methods. However, I highly recommend Spelling Power. One word of caution. If your child does not seem to respond to a multisensory program, choose one of the components of the program and see if that is more effective. One time, our foster son, who I will call John, was getting bogged down with spelling using Spelling Power. Another way to find out if your child has learned the information is to reverse roles. Have your child be the teacher teaching you the math concept. This will allow you to test how well he understands and reinforce correct understanding. Children love to be the teacher or to have a secretary. This will allow you to test and reinforce in a game format. You definitely do not have to use a standard paper and pencil test to find the information you need. If you choose to teach spelling, math facts, or whatever without a curriculum, use a stack of index cards and a black magic marker to make cards. Input this information frequently throughout the day. If your child is somewhat independent, you could have her input this information to herself by reading it aloud between each of her subjects. Eventually, you will have 3 different stacks, one that should be reviewed multiple times throughout the day. Second, you will have one that she reviews once a day. Finally, you will have a big stack that you will check periodically to see if that information needs to start over in the frequent or daily stack. There are a variety of ways to reinforce learning. The effective teacher will soon learn what will work with their child and may employ some of these methods at different stages in their child's learning experience. Why teacher stickers could be the best way to reinforce learning. They can be used at any stage. Teacher stickers can be used to reward both primary and secondary school learners. Unlike using other material or monetary rewards, in this method, it is the message that the sticker carries that matters, and not necessarily the value of the sticker. The learner receiving the reward feels that they are recognized and that they are unique at whatever level they may be. Stickers stand no chance of being viewed as insufficient to reward the achievement in question. Stickers for schools are unique. Rewards are the most effective when they are unique. It is not a bad idea to give gifts or any other material thing to appreciate the exemplary performance of a learner. However, it is most unlikely that such a presentation will be totally unique. Stickers, on the other hand, will contain an appreciation message that is particular to the achievement in question. For example, the top student in the first term of the year 2011, if given a sticker for that, may have it with the following words: Top Student, First Term 2011. In addition, it could even bear the name of the student being rewarded. This is a situation where no one else ever had such a sticker, neither will there be one in the future. That uniqueness makes them feel great, unique, and highly motivated. Stickers can be used in various ways. The power of reward stickers lays in the fact that they can be used in many different ways. Most teachers love putting them on test papers before giving the papers back to the learners. Others have come up with very creative ways, like designing badges on which the stickers are pasted. The student then wears the badge and lets everyone appreciate their achievement. A sticker can also be put on a certificate. That would go a step further in motivating the learners. Giving the learners a sticker book on which they add a sticker every time they do well, or creating a board with the name of students and stickers beside them for all their achievements are some of the other ways. The methods are simply inexhaustible, and they can go as far as the teacher's creativity can take them. They have long-lasting effects. It would be of little use to motivate a pupil for a short term only. The most effective rewards are those that have been given lasting effects after the reward has been given. That is one outstanding characteristic of reward stickers. The pupil can keep them and derive motivation from them for months or years that follow. It is not always about positive rewarding. There have been a lot of debate about how misbehaving students should be handled. A universally accepted idea is that withdrawing something that a child likes makes them realize that there are undesirable consequences of misbehaving. This is where the stickers come in. A teacher makes a chart on which well-behaving children get stickers to their names. Whenever the student misbehaves, a sticker is removed from their name and they are told why that is done. People have different opinions about the use of teacher stickers to reinforce the learning process, but it is no doubt that this method has stood out to be among the best. The fact that it has been used for a really long time tells a lot about its effectiveness. They become even more effective when they are used with school postcards that reach the parents directly. Most parents have appreciated them and agree that they go a great way in motivating young children. Even though stickers for schools are really simple and can nowadays be easily found on the internet, they are indeed very useful. The great thing about them is that they change with time and technology, such that a teacher does not have to use outdated stickers. A sticker customized for a specific student will no doubt bring a smile on that student's face, and do so for a long time after the day they got the sticker. Writing group leaders. Engage your members, reinforce learning. Writing group leaders have a unique opportunity each time they present information and resources to their members. Successful facilitation of group meetings can be enhanced by adhering to several presentation guidelines. Introduce your topic. This can include using an opening exercise that is related to the subject of the meeting. You could summarize activities from a previous meeting that are relevant and can be connected to what they are about to learn. For example, members may have been assigned to bring journal notes they recorded since the last meeting. Their assignment during the meeting would be to pick 3 to 5 related points from several of their journal entries to create a 250 to 300 word short story around the subject of the entries. You could also begin by asking 1 or 2 lead questions specific to the topic you plan to introduce that will encourage members to talk about experiences they have had and may lead to another quick writing exercise. Your goal is to manage their expectations of the group meeting and address any challenges individuals may express about the meeting topic. Explain the learning process. Summarize the group training exercise, including objectives and how the specific methods or strategies will be used. For example, survey questionnaires, group discussion, critique sessions, or free-flow writing. If there is need for someone to record responses or act as a timekeeper, these points should be made clear at the beginning by asking for volunteers. If group members are expected to move around and interact with one another, explain why and for how long. It's important for you as group leader to paint a picture of what you expect from your group during their meeting. Be energetic, speak clearly, and provide as much detail as possible so participants can visualize what they will be doing before they begin. Lack of understanding your directions or purpose can create member hesitation to participate. Your goal is to leave nothing to chance. Debrief the activity. Immediately after the activity, group leaders should take time for a short discussion of what took place. Questions can include, what did they think about the activity? What did they learn about themselves during the activity? What did they learn about each other? Can they use what they learned to improve their writing skills? If there are specific outcome measures, tips, and strategies that would be beneficial to the group, leaders should help members identify these points by emphasizing how these strategies and tips will be applicable to improving the way members complete tasks in the future. Connect the dots. Training exercises should not be standalone activities. They should serve a purpose by providing a summary of all the topics your group has been exposed to thus far. It is the responsibility of the group leader to combine precious assignments and session topics and demonstrate a progression or conclusion so members can leave the meeting with assignments leading to improvement or change. The goal is to help members improve their personal production as writers. By connecting the dots, members will be able to realize a level of closure to one process while preparing them to begin something new. When facilitating training exercises, group leaders should never forget their value to the process. Always start with the end in mind. Enjoy the in-between, but remember you are the catalyst for growth in others. Artificial intelligence, reinforcement learning. Complete Guide to Artificial Intelligence and Machine Learning. When people talk about artificial intelligence, they usually don't mean supervised and unsupervised machine learning. These tasks are pretty trivial compared to what we think of AIs doing. Playing chess and Go, driving cars, etc. Reinforcement learning has recently become popular for doing all of that and more. Reinforcement learning opens up a whole new world. It's led to new and amazing insights both in behavioral psychology and neuroscience. It's the closest thing we have so far to a true general artificial intelligence, and this course will be your introduction. Access 71 lectures and 5.5 hours of content 24/7. Discuss the multi-armed bandit problem and explore exploit dilemma. Learn ways to calculate means and moving averages and their relationship to stochastic gradient descent. Explore Markov decision processes, dynamic programming, Monte Carlo, and temporal difference learning. Understand approximation methods. Description. Reinforcement learning has recently become popular for doing all of this and more. Much like deep learning, a lot of the theory has been discovered in the 70s and 80s, but it hasn't been until recently that we've been able to observe firsthand the amazing results that are possible. Reinforcement learning is difficult for a number of reasons. The blame attribution problem is the problem of determining which action was responsible for a reward or punishment. The responsible action may have occurred a long time before the reward was received. Moreover, not a single action, but rather a combination of actions carried out in the appropriate circumstances may be responsible for the reward. For example, you could teach an agent to play a game by rewarding it when it wins or loses. It must determine the brilliant moves that were needed to win. You may try to train a dog by saying "bad dog" when you come home and find a mess. The dog has to determine, out of all of the actions it did, which of them were the actions that were responsible for the reprimand. Even if the dynamics of the world does not change, the effect of an action of the agent depends on what the agent will do in the future. This is common among planning problems, but it is complicated in the reinforcement learning context because the agent does not know, a priori, the effects of its actions. The explore-exploit dilemma. If the agent has worked out a good course of actions, should it continue to follow these actions, exploiting what it has determined, or should it explore to find better actions? An agent that never explores may act forever in a way that could have been much better if it had explored earlier. Introduction to dynamic programming. Let us say that we have a machine, and to determine its state at time t, we have certain quantities called state variables. There will be certain times when we have to make a decision which affects the state of the system, which may or may not be known to us in advance. These decisions or changes are equivalent to transformations of state variables. The result of the previous decisions help us in choosing the future ones. What do we conclude from this? We need to break up a problem into a series of overlapping subproblems and build up solutions to larger and larger subproblems. If you are given a problem which can be broken down into smaller subproblems, and these smaller subproblems can still be broken into smaller ones, and if you manage to find out that there are some overlapping subproblems, then you've encountered a DP problem. Some famous dynamic programming algorithms are 1. Unix diff for comparing two files, 2. Bellman-Ford for shortest path routing in networks, 3. TeX, the ancestor of LaTeX, and 4. WASP, winning and score predictor. The core idea of dynamic programming is to avoid repeated work by remembering partial results, and this concept finds its application in a lot of real-life situations. In programming, dynamic programming is a powerful technique that allows one to solve different types of problems in type O(n)(2) or O(n)(3), for which a naive approach would take exponential time. Dynamic programming and recursion. Dynamic programming is basically recursion plus using common sense. What it means is that recursion allows you to express the value of a function in terms of other values of that function, where common sense tells you that if you implement your function in a way that the recursive calls are done in advance and stored for easy access, it will make your program faster. This is what we call memoization. It is memorizing the results of some specific states, which can then be later accessed to solve other subproblems. The intuition behind dynamic programming is that we trade space for time. In other words, to say that instead of calculating all the states taking a lot of time but no space, we take up space to store the results of all the subproblems to save time later. Majority of the dynamic programming problems can be categorized into two types. 1. Optimization problems, and 2. Combinatorial problems. The optimization problems expect you to select a feasible solution so that the value of the required function is minimized or maximized. Combinatorial problems expect you to figure out the number of ways to do something or the probability of some event happening. Every dynamic programming problem has a schema to be followed. Show that the problem can be broken down into optimal subproblems. Recursively define the value of the solution by expressing it in terms of optimal solutions for smaller subproblems. Compute the value of the optimal solution in a bottom-up fashion, and construct an optimal solution from the computed information. What is a dynamic programming? How can it be described? A DP is an algorithmic technique which is usually based on a recurrent formula and one or some starting states. A subsolution of the problem is constructed from a previously found one. DP solutions have a polynomial complexity which assures a much faster running time than other techniques like backtracking, brute force, etc. Now let's see the base of DP with the help of an example. Given a list of n coins and their values, v1, v2, all the way to vn, and the total sum s. Find the minimum number of coins the sum of which is s. We can use as many coins of one type as we want. Or report that it's not possible to select coins in such a way that they sum up to s. Now, let's start constructing a DP solution. First of all, we need to find a state for which an optimal solution is found, and with the help of which we can find the optimal solution for the next state. What does a state stand for? It's a way to describe a situation, a sub-solution for the problem. For example, a state would be the solution for the sum I, where I is less than or greater to s. A smaller state than the state I would be the solution for any sum j, where j is less than I. For finding a state I, we need to find first all the smaller states j, where j is less than I. Having found the minimum number of coins which sum up to I, we can easily find the next state, the solution for I plus 1. How can we find it? It is simple. For each coin j, vj is less than or equal to I, look at the number of minimum coins found for the I vj sum. We have already found it previously. Let this number be m. If m plus 1 is less than the minimum number of coins already found for the current sum I, then we write the new result for it. For a better understanding, let's take this example. Given coins with the values 1, 3, and 5, and the sum s is set to be 11. First of all, we mark that for the state 0, sum 0, with a minimum number of 0 coins. Then we go to sum 1. First, we mark that we haven't found a solution for this one. The value of infinity would be fine. Then we see that only coin 1 is less than or equal to the current sum. Analyzing it, we see that for sum 1 minus v1 equals 0, we have a solution with 0 coins. Because we add 1 coin to this solution, we'll have a solution with 1 coin for sum 1. It's the only solution yet found for this sum. We'll write or save it. Then we proceed to the next state, sum 2. We again see that this is the only coin which is less or equal to this sum is the first coin, having a value of 1. The optimal solution found for sum 2 minus 1 equals 1 is coin 1. This coin 1 plus the first coin will sum up to 2, and thus make a sum of 2 with the help of only 2 coins. This is the best and only solution for sum 2. Now, we proceed to sum 3. We now have 2 coins which are to be analyzed, first and second one having values of 1 and 3. Let's see the first one. There exists a solution for sum 2, 3 minus 1, and therefore we can construct from it a solution for sum 3 by adding the first coin to it. Because the best solution for sum 2 that we found has 2 coins, the new solution for sum 3 will have 3 coins. Now let's take the second coin with a value equal to 3. The sum for which this coin needs to be added to make 3 is 0. We know that sum 0 is made up of 0 coins. Thus, we can make a sum of 3 with only 1 coin, 3. We see that it's better than the previously found solution for sum 3, which was composed of 3 coins. We update it and mark it as having only 1 coin. The same we do for sum 4, and we get a solution of 2 coins, 1 plus 3, and so on. Having understood the basic way a DP is used, we may now see a slightly different approach to it. It involves the change or update of best solution yet found for sum I, whenever a better solution for this sum was found. In this case, the states aren't calculated consecutively. Let's consider the problem above. Starting with having a solution of 0 coins for sum 0, now let's try to add the first coin with value 1 to all sums already found. If the resulting sum t will be composed of fewer coins than the previous one found, we'll update the solution for it. Then we do the same thing for the second coin, third coin, and so on for the rest of them. For example, we first add coin 1 to sum 0 and get sum 1. Because we haven't yet found a possible way to make a sum of 1, this is the best solution yet found, and we mark S1 equals 1. By adding the same coin to sum 1, we'll get sum 2, thus making S2 equals 2. And so on for the first coin. After the first coin is processed, take coin 2, having value of 3, and consecutively try to add it to each of the sums already found. Adding it to 0, a sum 3 made up of 1 coin will result. Till now, S3 has been equal to 3, thus the new solution is better than the previously found one. We update it and mark it S3 equals 1. After adding the same coin to sum 1, we'll get a sum 4 composed of 2 coins. Previously, we found a sum of 4 composed of 4 coins. Having now found a better solution, we update S4 to 2. The same thing is done for the next sums. Each time a better solution is found, the results are updated. Temporal difference learning. The temporal difference methods TD and SARSA form a core part of modern reinforcement learning. Their appeal comes from their good performance, low computational cost, and their simple interpretation, given by their forward view. Recently, new versions of these methods were introduced, called True Online TD and True Online SARSA, respectively. These new versions maintain an exact equivalence with the forward view at all times, whereas the traditional versions only approximate it for small step sizes. We hypothesize that these true online methods not only have better theoretical properties, but also dominate the regular methods empirically. In this chapter, we put this hypothesis to the test by performing an extensive empirical comparison. Specifically, we compare the performance of true online TD over SARSA with regular TD over SARSA on random MRPs, a real-world myoelectric prosthetic arm, and a domain from the arcade learning environment. We use linear function approximation with tabular, binary, and non-binary features. Our results suggest that the true online methods indeed dominate the regular methods. Across all domains and representations, the learning speed of the true online methods are often better, but never worse than that of the regular methods. An additional advantage is that no choice between traces has to be made for true online methods. Besides the empirical results, we provide an in-depth analysis of the theory behind true online temporal difference learning. In addition, we show that true online temporal difference methods can be derived by making changes to the online forward view and then rewriting the update equations. Terms of reinforcement learning. Reinforcement learning. Remember how you learned to ride a bike? More than likely, an adult stood or walked behind you and encouraged you to make the first moves on your bike and helped you get going again when you stumbled or fell. But it is very difficult to explain to a child how to ride a bike, and even a good explanation makes little sense to someone who has never ridden before. You have to get the feel for it. So how did you learn to ride a bike if it could not be clearly explained? Well, you just tried to ride the bike, and more than likely, you fell, or at least stopped abruptly and had to catch yourself. You fell or stumbled repeatedly until you got some little spark of success after riding for a few meters before you fell again. During this learning process, the feedback signals that tell us how well we do are either pain, ouch, I fell, that hurts, I will avoid doing what led to this next time, or reward. Wow, I'm riding the bike. This feels great. I just need to keep doing what I'm doing right now. In a reinforcement learning problem, we take the view of an agent that tries to maximize the reward that is receiving from making decisions. Thus, an agent that receives the maximum possible reward can be viewed as performing the best action for a given state. An agent here refers to an abstract entity, which can be any kind of object or subject that performs actions. Autonomous cars, robots, humans, customer support chatbots, Go players. The state of an agent refers to the agent's position and state of being in its abstract environment. For example, a certain position in a virtual reality world, a building, a chessboard, or the position and speed on a racetrack. To simplify the problem and the solution of a reinforcement problem, the environment is often simplified so that the agent only knows about the details which are important for decision-making, while the rest is discarded. Just like in the bike riding example, the reinforcement algorithm only has two sources of feedback to learn from: the penalty, pain of falling, and reward, thrill of riding for a few meters. If we view penalty as negative reward, then the whole learning problem concerns exploring an environment and trying to maximize the reward that our agent receives for passing from state to state, until a goal state is reached: driving autonomously from A to B, winning a chess game, solving a customer problem via chat. This is reinforcement learning in a nutshell. The value function. Reinforcement learning is about positive and negative rewards, punishment or pain, and learning to choose the actions which yield to the best cumulative reward. To find these actions, it's useful to first think about the most valuable states in our current environment. For example, on a racetrack, the finish line is the most valuable. That is the state which is most rewarding. And the states which are on the racetrack are more valuable than states that are off track. Once we have determined which states are valuable, we can assign rewards to various states. For example, negative rewards for all states where the car's position is off track, a positive reward for completing a lap, a positive reward when the car beats its current best lap time, and so on. We can imagine the states and rewards as a discrete function. For example, a racetrack could be represented by a grid of 1 by 1 meter tiles. The rewards on a tile are represented by numbers. For example, the goals might have a reward of 10, and the tiles which are off track have a reward of -2, while all other tiles have a reward of 0. If we picture this function in 3 dimensions, then we can imagine that the best action is to stay as high as possible, maximize reward. Discounting factor. Even though the value function handles competing rewards, it also depends on a parameter called the discounting factor, which defines its exact behavior by limiting how much an agent is affected by rewards which lie in the far future. This is done by multiplying the partial reward by the discounting factor whenever a state change is made. So, with a discounting factor of 0.5, the original reward will be 1/8 of its value after only 3 state changes, causing the agent to pursue rewards in close proximity rather than rewards which are further away. Thus, the discounting factor is a weight that controls whether the value function favors prudent or greedy actions. For example, A race car might get a high reward by going fast, so a very greedy decision with discount factor close to 0 might always go as fast as possible. But a more prudent agent knows that going as fast as possible is a bad idea when there's a sharp turn ahead, while slowing down at the right moment may yield a better lap time later, and thus a higher reward. To have this foresight, the agent needs to receive the reward for going faster later, so a discounting factor closer to 1 may be better. The value function's discounting factor ensures that rewards that far away diminish proportionally to the distance, or steps it takes to reach them. This factor is usually set to a value which values long-term rewards highly, but not too high. For example, the reward decays by 5% per state transition. The algorithm learns the specific partial reward value of each state of the value function by first initializing all states to 0, or their specific reward value, and then searching all states and all their possible next states and evaluating the reward if it would get to the next states. If it gets a partial reward in the next state, it increases the reward of the current state. This process repeats until the partial reward within each state doesn't change anymore, which means that it has taken into account all possible directions to find all possible rewards from all possible states. You can see the process of this value iteration algorithm in Figure 1. This may seem inefficient at first, but a trick associated with dynamic programming makes it much more efficient. Dynamic programming solves higher-order problems in terms of already solved subproblems. The computer reward for going from state B to C can be reused in computing the reward for state chains ABC and DBC. In summary, the value function and value iteration provides a map of partial rewards, which guides the agent towards rewarding states. The policy function. The policy function represents a strategy that, given the value function, supports the action believed to yield the highest long-term reward. Often, there is no clear winner among the possible best actions. For example, the agent might have the choice to enter one of 4 possible next states, A, B, C, and D, with reward values A equals 10, B equals 10, C equals 5, and D equals 5. So both A and B would be good immediate choices, but a long way down the road, action A might actually have been better than B, or action C might even have been the best choice. It is worth exploring these options during training, but at the same time, the immediate reward values should guide the choice. So how can we find a balance between exploiting high reward values and exploring less rewarding paths which might return high rewards in the long term? A clever way to proceed is to make choices with a probability proportional to the reward. In this example, the probability of taking A would be 33%, 10 divided by 10 plus 10 plus 5 plus 5, and the probability of taking B, C, and D would be 33%, 16%, and 16% respectively. This random choice nature of the policy function is important to learn a good policy. There might exist effective or even essential strategies that are counterintuitive but necessary for success. For example, if you train a race car to go fast on a racetrack, it will try to cut the corners with the highest speed possible. However, this strategy will not be optimal if you add competitors to the mix. The agent then needs to take into account these competitors, and might want to take the turn slower to avoid the possibility of a competitor overtaking, or worse, a collision. Another scenario might be that cornering at very high speed will wear the tires much quicker, resulting in the need for a pit stop, costing valuable time. Note that the policy and value functions depend on each other. Given a certain value function, different policies may result in different choices, and given a certain policy, the agent may value actions differently. Given the policy just win the game for a chess game, the value function will assign a high value to the moves in the game which have a high probability of winning. Sacrificing chess pieces in order to win safely would be valued highly. but given the policy win with a large lead or not at all, then the policy function will just learn to select the moves which maximize the score in a particular game, or never sacrifice chess pieces. These are just two examples of many. If we want to have a specific outcome, we can use both the policy and value functions to guide the agent to learn good strategies to achieve that outcome. This makes reinforcement learning versatile and powerful. The Q function. We've seen that the policy and value functions are highly interdependent. Our policy is determined mostly by what we value, and what we value determines our actions. So maybe we could combine the value and policy functions. We can, and that combination is called the Q function. The Q function takes both the current state, like the value function, and the next action, like the policy function, and returns the partial reward for the state-action pair. For more complex use cases, the Q function may also take more states to predict the next state. For example, if the direction of movement is important, one needs at least two states to predict the next state, since it is often not possible to infer precise direction from a single state. For example, a still image. We can also just pass input states to the Q function to get a partial reward value for each possible action. From this, we can, for example, randomly choose our next action with the probability proportional to the partial reward, or exploration, or just take the highest valued action, or exploitation. However, the main point of Q function is actually different. Consider an autonomous car. There are so many states that it is impossible to create a value function for them all. It would take too long to compute all partial rewards for every possible speed and position on all the roads that exist on Earth. Instead, the Q function, 1, looks at all possible states that lie one step ahead, and 2, look at the best possible action from the current state to that next state. So, for each next state, the Q function has a look ahead of one step, not all possible steps until termination, like the value function. These look-aheads are represented as state-action pairs. For example, state A might have 4 possible actions, and so that we have the action pairs A to B, A to C, and A to D. With 4 actions for every state and a 10 by 10 grid of states, we can represent the entire Q function as 4 10 by 10 matrices, or one 10 by 10 by 4 tensor. See Figure 3 for a Q function which represents the solution to a grid world problem, a 2D world where you can move to neighboring states, where the goal is located in the bottom right corner. In some cases, we need to model sheer infinite states. For example, in an autonomous car, the state is often represented as a continuous function, such as a neural network, which just takes all the state variables, such as speed and position of the car, and outputs Q values for each action. So why does it help to have information about only some states? Many states are very well correlated, so the same action was taken at 2 different but similar states may lead to success in both cases. For example, every turn on a racetrack will be different, but the things that you learn from each left turn, when to start the turn, how speed should be adjusted, etc., are valuable for the next left turn. So over time, a car-driving agent can learn to make better and better left turns, even on tracks it has never seen. Q-learning. To train the Q function, we initialize all Q values of all state-action pairs to 0, and initialize the states with their given rewards. Because the agent does not know how to get to the rewards, an agent can only see the Q value of the next states, which will all be 0. The agent may go through many states until it finds a reward. Thus, we often terminate training the Q function after a certain length, for example 100 actions, or after a certain state has been reached, 1 lap on a racetrack. This ensures we don't get stuck in the process of learning good actions for one state, since it's possible to be stuck in a hopeless state where you can make as many iterations as you like and never receive any noticeable rewards. Learning the Q function proceeds from the end, the reward, to start, the first state. Figure 4 depicts the grid world example from Figure 1 in terms of Q learning. Assume the goal is to reach the goal state G in the smallest number of steps. Initially, the agent makes random moves until it accidentally reaches either a trap or the goal state. Because the traps are closer to the start state, the agent is most likely to hit a trap first. But this pattern is broken once the agent stumbles upon the goal state. From that iteration on the states right before the goal state, one step look ahead, have a partial reward, and since the reward is now closer to the start, the agent is more likely to hit such a rewarding state. In this way, a chain of partial rewards builds up more quickly, and the more often the agent receives a partial reward state, so the chain of partial rewards from goal to start state is quickly completed. Deep Q learning. An autonomous vehicle may need to consider many states. Every different combination of speed and position is a different state, but most states are similar. Is it possible to combine similar states so that they have similar Q values? Here is where deep learning comes into play. We can input the current point of view of the driver, an image, into a convolutional neural network, or CNN, trained to predict the rewards for the next possible actions. Because images for similar states are similar, many left turns look similar, they will also have similar actions. For example, a neural network will be able to generalize to many left turns on a racetrack and even many appropriate actions for left turns that were not encountered before. Just like a CNN trained on many different objects and images can learn to correctly distinguish those objects, a network trained on many similar variations of left turns will be able to make fine adjustments of speed and positions for each different left turn it is presented. To use Q learning successfully, however, we cannot simply apply the rule to train Q function described previously. If we apply the Q learning rule blindly, then the network will learn to do good left turns while doing left turns, but will start forgetting how to do good right turns at the same time. This is so because all actions of the neural network use the same weights, turning the weights for left turns making them worse for other situations. The solution is to store all the input images and the output actions as experiences, that is, store the state, action, and reward together. After running the training algorithm for a while, we choose a random selection from all the experiences gathered so far and create an update for neural network weights, which maximizes Q values, or rewards, for all actions taken during those experiences. This way, we can teach our neural network to do left and right turns at the same time. Since very early experiences of driving on a racetrack are not important, because they come from a time where our agent was less experienced, or even a beginner, we only keep track of a fixed number of past experiences and forget the rest. This process is termed experience replay. AlphaGo. AlphaGo, developed by Google DeepMind, made big news in 2016 by becoming the first computer program to beat a human professional player at the game of Go. It then went on to beat Lee Sedol, one of the top Go players in the world, 4 games to 1. AlphaGo combines many of the elements previously mentioned in this chapter, namely 1. Value, and 2. Policy neural networks, which represent 1. The value function over the current configuration in a Go game, and therefore predicts the relative value of one move over another, and 2. The policy function which suggests what move should be picked in order to win the game. These networks are convolutional networks, which treat the Go board as a 19 by 19 input image, 1 pixel for each position. GED study tip. For real knowledge, reinforce the learning process. Once GED students discover how to activate the learning process, it equally becomes important to reinforce learning, since real learning happens when you use knowledge, especially if it's fresh. And since learning is really a lifelong process, lessons on how people learn and continue to learn are good ones to understand. People learn faster and better when they control the speed of learning. In most classrooms, it's the teacher who controls the material, so it's important for GED students to determine their own learning speed and to devise methods or a study plan that accommodates that speed. The self-study guide is a good way to control the speed and pace of learning. But when self-directing a study program, it's important to make the study a habit, whether short periods for studying are set aside for each day, or longer periods 2 to 3 times a week. In classroom situations, it's much more difficult to control the speed of learning since instructors follow lesson plans. So, talking to the instructor may help. Just explain that you need a different learning pace. Some students may learn better by moving more quickly through the material, while others need extra time. Regardless, once a student understands that they need to control their own learning and the speed in which it takes place, learning is easier. They can then identify the most comfortable speed and consequently learn faster and learn more. Learning requires rapid feedback. Feedback is a critical part of the learning process, one that's often overlooked. The more immediate and meaningful the feedback is, the quicker people learn. Consider how many classroom situations work. Information is presented over days or weeks, or sometimes even months. Then students are tested. Until they see test results, students may not know whether their learning is effective. The best learning situation gives the learner immediate feedback on their progress. A good GED study program should include continuous opportunities and methods for students to connect their learning efforts with their outcomes. This way, students quickly identify whether they've learned the material or need to learn it better. Meaningful feedback also reinforces the learning process because information is used quickly and frequently. It's the key to keeping new information, retaining it instead of just remembering it. Real learning means real knowledge. Use it. Once you learn material and gain new knowledge, use it. Use it every chance you get. Using new knowledge ensures ownership and enhances critical thinking skills, the most important skills measured by the GED. Here is a good example of how one successful past GED student gained real knowledge through the application of it. Maria, studying for the GED Language Arts Reading Test, encountered an unfamiliar word in a literary passage, the word superfluous. Initially, the word just seemed confusing. She wanted to check the word in a dictionary, but remembered that she wouldn't be able to take a dictionary to the official GED test site. And she had learned in her online GED class how to look for context clues to find word meanings, especially if the word seemed to be key to the passage. Maria found 3 words that seemed to point back to superfluous. One word was extra, another overabundant, and the other excessive. Maria also saw that superfluous had a root of super, which seemed very similar in meaning to the other 3 words. So she was sure that she was right. Her dictionary confirmed it. Through the next few weeks, Maria began using new words she was learning during conversations. After a short time, these new words came to her more naturally. She developed complete ownership of her new knowledge. Not only was her vocabulary expanding, she discovered that it became easier to move through language arts passages. Her feedback scores were climbing. Also, the essay portion of the exam suddenly seemed much less challenging. Maria was delighted. She wasn't just pleased with her new ability, her studies now seemed more like a hobby instead of a chore, and she wasn't the only one impressed. Toddler. Positive reinforcement. An age of innocence and purity are found in toddlers. Toddlers want to explore the world and surroundings around them. As they learn to walk, they face the world at a minimal height, exploring and seeking as they set off in their daily journeys. Just imagine for a second viewing the world from knee height, not knowing right from wrong, and having to learn along the way. Learning what is okay to do, touch, and play with is an everyday experience for a toddler. This age is very important in developing positive methods of meeting new boundaries and limits within the toddler. Setting these boundaries and limits enables positive reinforcement and gives toddlers familiarity and security. Knowing what is okay to discover and learn opposed to what is harmful and off limits are all important for a toddler to learn. Repetition of praise when a toddler is discovering and learning safe environments should be done in a reinforcing positive behavior. This repetition will raise the self-esteem of the toddler, knowing they are choosing the correct path, causing a positive reaction. By embracing the child or talking to them in a positive manner, they will soon learn that their actions while discovering their limits are on the right track. Removing the toddler and stating with a firmness that their actions are not acceptable or dangerous is the correct method when they stumble on a negative track. Being consistent on both the positive and negative actions with the toddler will have constructive behavior reaction from the toddler. Once toddlers are into the walking stage of life, their environment is their playground. Not having the skills and experience to determine which exposures are safe and which are dangerous means continuous supervision and guidance. Through supervision and guidance, toddlers will discover that praise is given when elders approve of their actions. From clapping, vocal confirmation, hugging, and other positive reinforcements, a toddler will develop pride and will want to please over and over again. It is human nature to receive praise and reward from actions and events endured in a day, from those we respect and love. While learning and exploring is an everyday occurrence for a toddler, it is the guidance received that teaches them the positive skills they need for the future. Through learning and exploring their environment, along with praise and reward, toddlers will learn what is acceptable and what is not acceptable. It will prepare and teach them that it is good to explore and learn, although not everything is safe to play or learn with. Having boundaries and guidance prepares them for the world ahead, with discovering, interacting, and exploring the world which is their new playground. This has been Reinforcement Learning, Artificial Intelligence, Schooling, and GED Study Tips. Written by David Feldspar. Narrated by Jason R. Gray. Copyright 2018 by David Feldspar. Production copyright 2018 by David Feldspar.